Hi everyone, Kevin here. We are back with some asynchronous work on polyphenolic compounds, part of module number 3. Let's get going. Let's start with the overall classes of phenolic compounds. So we know all phenolic compounds are characterized by at least one conjugated 6-carbon ring with one hydroxyl group on it. So that defines phenol itself. And polyphenolic compounds in wine contain at least one phenol-based structure. We don't find phenol itself in wine, but we find polyphenolic compounds based on phenol. The overall group of phenolic compounds are broken into two subgroups, two major subgroups, non-flavonoids and flavonoids. Flavonoids are characterized by this 3-ring system that consists of 6 carbons in ring A, 3 carbons in ring C, and 6 carbons in ring B. So you'll see this 6-3-6 structure repeated over and over again. Sometimes there's different positioning of the B ring. Sometimes it can be at position 3 here, but you see the basic 3-ring structure repeating in flavonoids. So they're based on flavin. There's the flavin ring, again the 6-3-6 structure. And flavin 3-ol, for example, is one of the common structures and forms the basis of lots of other compounds. So flavin 3-ol with that extra hydroxyl group there, or that, not extra in this picture, but the one hydroxyl group showing at position 3 on the C ring. Here are the non-flavonoids, and they're broken down into 3 categories. I want to tell you a little bit about each one of these categories, okay? The first category is hydroxycinamic acids. These are important because they are antioxidants, and you hear them a lot when you look at the literature. If you ordered an analysis of phenolic compounds from ETS, say you wanted to have them analyze your wine for you, you would see they would come back and tell you the amount of hydroxycinamic acids in your wine. And one big example of that, the most common one, is caphtoric acid. And caphtoric acid is actually has a couple of pieces to it. Look at that piece there is the phenolic piece, right? It's defined by phenol. That's our phenol right there. I'm circling. That's the core phenol structure. Look at this other part of the molecule in caphtoric acid over here. This part actually overlaps a bit with the first part. That is tartaric acid, the main acid in wine. So tartaric acid joins with this other part of the molecule to form caphtoric acid. And you'll see nature often do that. Nature will reuse parts of molecules. They'll join together. Sugars will sometimes join with polyphenolic compounds. And sometimes sugars will be independent, and that's what the yeast eat. So you'll see nature reusing some of these pieces, and that's an interesting example of that, where tartaric acid, the main acid, one of the 2 main acids in wine, will join with a polyphenolic compound to make these hydroxycinamic acids. These have antioxidant properties, and that makes them somewhat important in wine. And these are also in both whites and reds. They come from the pulp, not from the skins. And so they have equal amounts in whites and reds. Hydroxycinamic acids are pretty equal in whites and reds. Second class, all right, so that was the first of the non-flavonoids. Second is very important, and those are the tannins that come from oak. And we call those hydrolyzable tannins only because they can be broken apart by water. That's the hydro part of hydrolyzable. So they can be broken apart by water. But the key thing is that they come from oak. And here are a couple of examples. You'll see ellagic acid, and you'll see vanillin. Vanillin smells like vanilla. So there is one example of where a phenolic compound actually has an impact on aroma. So vanillin smells, as you would expect, like vanilla. And here's an example of those. Don't worry at all about these huge chemical structures. Just know that you get tannins from oak. And tannins from oak can be important for a couple of reasons, and I'll talk about those soon. But the short answer is they're important in in color stability, and they're important in sensory impact in the mouth. All right, so tannins from oak. Third category are what we call still beans. A key example of that is a molecule called resveratrol. You may have heard of that. It's getting a lot of press because it has a lot of, it's anticipated to have many health benefits. The science is still out, but the evidence suggests that this could be important as an antioxidant in maybe fighting cancer and fighting all kinds of diseases. The science also suggests that you need an awful lot of resveratrol in your diet to get health benefits, a lot more resveratrol than you'd find in a typical glass of wine. But there's a lot of research being done. Because it has potential health benefits, people are very interested, obviously, in this compound. So you'll see resveratrol in the next probably 10 years getting a lot of research, getting some press. We may find out it's very important. We may find out that the levels in wine are so low that it's not very important. But it's a key class of the non-flavonoids. So here's a summary of the importance of that group, the non-flavonoids. They're antioxidants, which is really important, have potential benefits on longevity of wine as well as on our health. There are potential other health benefits as well from things like resveratrol, so they may be anti-cancer. Resveratrol may be an anti-cancer agent. And then third important thing is the oak tannins, as I mentioned, impact both mouthfeel and color stability. And on the mouthfeel, you often get oak tannins plus tannins from the wine getting together. So I'll call them oak tannins plus grape tannins together, leading to a very nice mouthfeel. And this will be why we often want to ferment whites and even reds in barrels, because you get this nice mouthfeel from those oak tannins. All right, that's it for the non-flavonoids. This slide is really key, just knowing that they have these three impacts. Talk about the second class then, the second major subgroup of phenolic compounds, and those are the flavonoids. Okay, so we just got through non-flavonoids. Now let's talk about flavonoids. We break down flavonoids into three key subgroups. Flavanols, which have an O here, Flavanols, which have an A here, and then anthocyanins, which are colored compounds. So we'll break down these three. If you're interested in the chemistry and identifying these, you can see that the flavanols are characterized by this double bond to oxygen right here. We're not going to talk much more about flavanols. They are antioxidants. They probably have a role in color stability, and they probably have a role, but they don't have a major sensory impact in our mouth. Okay, so antioxidants, color stability, no major sensory impact. We're done talking about flavanols. Anthocyanins are the colored compounds, and they're characterized by this positive charge. So you'll see this positive charge on the oxygen, and that's part of what gives them the ability to absorb light in the range, the visible range in which our eye sees that light, and that's why these are colored. They absorb certain light, they reflect other light, and our eye sees that other reflected light as red. Okay, so these are the red compounds in grape skins that give red wine our color. The flavanols, those are the ones that will polymerize to form large tannins. And again, you see that classic 6-3-6 ring structure that you see also in the anthocyanins and the flavanols, but you don't see that positive charge on the oxygen like you do in anthocyanins. Have the positive charge, flavanols do not. And you don't see that double bond to oxygen at this position. All right, the flavanols over here have the double bond to oxygen right there, and the flavanols do not. Okay, let's do anthocyanins. Anthocyanins are the colored molecules. Here's the basic structure. All right, that 6-3-6 ring structure, 6-3-6. 6, and there's that positive charge on oxygen. And look at this molecule. It shows two groups, R1 and R2. And here is the definition of some of the common R structures that are found in wine. If R1 is a hydrogen and R2 is an OH group, that's a molecule called cyanidin. One of the most important colored molecules is malvidin, this last one here. The R1 group and the R2 group are identical. So if you had malvidin, you would see this OCH3 group. You would see that at this spot, and you'd also see it over here at this spot. Okay? The key take-home is these are colored, and these give wine its characteristic red color. All right? Anthocyanins, colored molecules, that's your real take-home. Sulfur dioxide can react with colored compounds at this position right here, and this one is colorless, where this one up here on the upper right is red. All right, so SO2 can bleach molecules. You can actually get anthocyanins binding with other anthocyanins, which prevents this reaction of sulfur dioxide. So you could have this molecule here, again, that's colored red. Instead of going in this direction, we could go in another direction, and we could add another anthocyanin, cyanin, or we could add another polyphenolic compound, and then we end up with a polymer, meaning our anthocyanin is joined to another molecule, and those polymers have stable color. So they would not be bleached by sulfur dioxide. So you have a couple choices. One, you can go in this direction and have sulfur dioxide bleach your anthocyanin so it's no longer red, it's now colorless. Or you can go in another direction when the anthocyanin actually polymerizes with other anthocyanins or other polyphenolic compounds to make nice stable color. And winemakers are interested in this because the expectation is the way we manage our wine in the tank and in the barrel can promote some of these polymers forming and avoid the colorless bleaching of compounds that you get from sulfur dioxide. If you soak your wine without sulfur dioxide, if you soak especially your red wine in contact with the skins, you get more, we believe, reactions in the polymer direction, and you get more stable color. So it may be something you think about as a winemaker. You may want to soak your wine in contact with the skins a little bit longer before you add sulfur dioxide. The risk, of course, is you could get some spoilage before you add sulfur dioxide, so there's a trade-off. Let's move on. Anthocyanins can also do copigmentation reactions. In that case, you get an anthocyanin molecule, which I'll just depict as a circle, and you can get them forming complexes where they actually will stack or otherwise associate with other molecules, and that can lead to stable color. All right, so copigmentation complexes can lead to stable color. Okay, and winemakers talk about this because we don't know a ton about the science yet, but we think that part of that cold soaking process, or potentially adding a little bit of white wine to red wine, some of those tricks may stabilize color by promoting copigmentation. Let's talk about the final class, and those are the Flavanols. Okay, so we talked about Flavanols just very briefly. We talked about colored compounds and anthocyanins. Now let's talk about the third class, Flavanols, and then we'll leave it at that. And thanks for hanging in. I know this is a long video. All right, Flavanols, you also see them called flavanthiols. You'll see that in the literature. If you go to seminars at UC Davis when they talk about phenolic compounds, you'll hear both of those terms. There's a couple places you find them. You find them in seeds and skins. In seeds, they tend to be smaller. There's monomers. So here's a monomer, meaning a single molecule. In this case, it's epicatechin. All right, that's a monomer. Down here below are polymers. All right, polymers. So here's our single molecule, and now it's joined via a chemical bond to another molecule with the same structure. And that in turn can be joined to another molecule with the same structure. And now you have multiple subunits making up one big molecule, and that would be a polymer. You can have a whole bunch of those. That number n there means that n can be one or could be hundreds. You can also have molecules joining at other positions like this dotted line shows over here. So these can get very complex in structure. When they get big, we refer to them as tannins. And remember in the last video we said that tannins are defined by their ability to tan hides, but we can't give you one structure of tannins because they're very complex like this. So tannins in seeds can be monomers, and those are often bitter. They're small, and they are more bitter in our mouth. Polymers that also come from seeds can actually be bigger. They average about 6 subunits. And the polymer of actually multiple, I changed the slide, so this is multiple subunits is shown at right, not just 2. These polymers that come from seeds are often sensed at the front of the mouth. We contrast this with the next slide, which the flavanols found in skins. Those are bigger. They average 27 subunits. In seeds it was small, average of 6. Now we have 27. These are sensed more at the back of the mouth, these big tannins. What's the significance there? Well, if a grape is a little underripe, potentially, you may be getting more tannins from the seeds, which are sensed at the front of your mouth. If the grapes are nice and ripe and the seeds are brown, the seeds are then going to release less of their tannins because of that brown hardening of the seed. And you'll sense more of the polymers just from skins, and they will be sensed at the back of your mouth. The polymers in seeds tend to be smaller. They tend to be larger in skins. Those large polymers are astringent, get the drying sensation, but not necessarily bitter. So a winemaker can manage this during extended maceration after the fermentation is complete, keeping the wine and the skins in contact. And during aging, you get this polymerization increasing, so the bitterness is reduced and astringency tends to soften. The big, complex polyphenolics are often softer. So bitterness goes down as things get bigger, and tannins get softer as things get bigger. And the more you can manage that in your wine, the more you can get a particular sensory impact. That's it for this video on phenolics. Thanks for watching, and see you in the next one.